Hello students, welcome back to my YouTube channel Physics Club by Shakti sir. So in today's lecture we will discuss few more numericals based on inelastic collision. So let's start with our first numerical. So first numerical says we have a bullet block system. So initially we have a block having mass is given, you can see it is 2.4 kg and a bullet having mass of 4.5 gram. So block is moving on a friction surface. There is a friction, that's why it is the coefficient of friction is also given. And once the bullet is inside the block, the bullet and block both combinedly move a distance of 1.8 meter before coming to rest. So what they are asking, what is the speed of the block immediately after the bullet come to rest within it. So they are asking the situation when the combined system, that is block and bullet inside it, start moving with some special velocity v dash. So they are asking the speed of that situation. So let's solve how we can discuss this. So you can see the combined mass travel a distance of 1.8 meter, this much, right? And here it is stopped. So it means that the final kinetic energy of the system is 0, but the initial kinetic energy is non-zero, because initially the system move with some this velocity, v dash velocity, okay, and the bullet was inside when they move with the v dash velocity. All right, so initially system has a kinetic energy, but finally there is no kinetic energy associated because the system come to at rest, and this kinetic energy is exhausted, you can say, is lost by the work done against the friction. So we can use here the work energy theorem. So use work energy theorem. So by the use of work energy theorem, we can easily calculate the speed. What is the work energy theorem? You know the change in kinetic energy is nothing but the work done by the friction in this situation. So actually the work energy theorem is the total work done by all the forces equals to change in kinetic energy, but here the only force acting is the frictional force. Okay, the change in kinetic energy, the situation says the kinetic energy change, the final kinetic energy which is 0, and the initial kinetic energy which we can write it as mass 1 plus mass 2, that is mass of bullet and block, and v dash square. This is the initial kinetic energy. It is equals to the work done. You can see the work done by the friction is negative, so negative friction multiply the displacement, which is 1.8 meter. Okay, this is our equation. Let's put the values. So it is negative 1 by 2 m1 plus m2 v dash square is equals to negative friction. So what's the value of friction? You can see the friction is nothing but mu times n, which is the normal force, and normal force can be written as m1 plus m2g. This is how we can write the normal force multiplied by the displacement. So in this situation you can easily cancel the masses term and the negative term from both sides. So what you get, the value of d, the situation now is v dash square. You can write 2 times of mu g d. So here v equals to square root of 2 mu g d. So by putting the suitable values, we can calculate the value of v or v dash. So let's substitute the value. So it is 2 multiply 0.2 multiply 9.8 multiply, it is 1.8. So you will get v dash is equals to 7.056. So v dash is equals to 2.656 meter per second. So this is the answer of part A. Now to solve the part B, and what is the part B? Part B is saying this is the part B, at what speed is the bullet fired? So actually they're asking the speed of the bullet. So let's say the speed of the bullet is u. Okay, so we can use the conservation of linear momentum. So conservation of linear momentum. So by the help of conservation of linear momentum, we can write the mass of the bullet and initial speed of the bullet, okay, is equals to mass of the bullet plus mass of the block and the final velocity of this combined system. Here the mass of the bullet we can calculate by just dividing the right side with the mass of the bullet, and we know the v dash value. Let's put the values. Once you put the values, you will get the answer. So m1 is nothing but so the combined mass you can put 0.4045. This is the combined mass of block and bullet, and v dash, which we just calculated, 2.656, all divided by m1, which is equals to 0.0045, right? So by calculating all this with your skills, you will get the answer of 1419.18 meter per second. So this is the initial speed of the bullet before colliding the block. So this is the answer of our question number first. Now we have question number 2. In question number 2, you can see two blocks, 2 kg, two 2 kg masses A and B collide. The velocities before the collision are this and this. So the velocities are given, right? And after the collision, they are asking what is the final velocity of B. So 3 velocities are given. What is the final velocity of B? So actually the situation is, let's say we have two blocks. This is our block A, this is our block B, right? And after the situation, this is our block A and this is our block B. Okay, so their initial velocities are given. So VA dash is given, VB dash is also given, and VA dash is also given. So we need to calculate what is our VB dash, this one. So how we can calculate this? We can calculate this with the help of conservation of linear momentum. So with the help of conservation of linear momentum, so let's write. So both masses are 2 kg, that is mass of A equals to mass of B equals to 2 kg. This is given. So mass is equal to 2, and this is VA vector plus again 2 multiply VB vector equals to mass of A multiply VA dash vector plus 2 multiply mass into velocity VB dash vector. So you can easily see here the two terms, these terms can cancel. So we have velocity of A. Velocity of A is 15 I cap plus 30 j cap, and velocity of V, which is we can write negative 10 I cap plus 5 j cap, and velocity of A is negative 5 I cap plus 20 j cap plus velocity of B dash. So let's solve this equation. What you will get? You will get 15 I cap minus 10 I cap equals to 5 I cap plus 35 j cap is equals to, here on the right side you have negative 5 I cap plus 20 j cap plus V dash B. Okay, so further you can say here it become 10 I cap plus 35 j cap minus 20 j cap equals to velocity of V dash. So it is 10 I cap plus 15 j cap is equals to velocity of B. Okay, so this is our velocity of B. That is the answer of our question part A. So this is the required answer of part A. Now let's move to the part B. How much kinetic energy was gained or lost in this collision? How much kinetic energy? So they are asking about the kinetic energy. So let's try to solve the kinetic energy. So initially the kinetic energy is again 1 by 2 mass and VA square plus 1 by 2 mass multiply VB square. This is the initial kinetic energy, right? So initially we have this much kinetic energy. You can see the mass is at 2 kg. So once you put the values 2, 2 and 2, 2 cancel. So you simply have VA square plus VB square. This is the value of initial kinetic energies. This is initial kinetic energy of the system. Why I cancel this 2 and this mass? Because mass is also 2 kg. So 2 and 2 cancel. Okay, so we have this situation. Similarly, we can calculate the final kinetic energy final. In the same way, the kinetic energy final will be VA dash square plus VB dash square. This will be our final kinetic energies. Let's calculate their values. What are their values? Okay, so VA dash plus VB dash, that is K initial, is equals to square root of, we have the value of VA, you can see this is the value of VA. So we will calculate their magnitudes. So the magnitudes of this is 15 square plus 30 square. Okay, and you will get, this is the square root of wait, so there is no need to write the square root because it is already squared. VA square, so it is 15 square plus 30 square. So you will get, and the VB, so what is VB? Look at here, VB, this one. So it is negative 10 square plus 5 square. So you will get 10 square plus 5 square. Okay, so we can calculate these situations. So it is 15 square, you will get 225. So 225 plus 900 plus 100 plus 25. So you can see it will be 1000 and 1250. This is what I get. So it is 1250 joule. This is the initial kinetic energy. Similarly, we can calculate the final kinetic energy of this situation, K final, which will be like this. Okay, so we have these values. VA dash, which is equals to 5 square plus 20 square. Why? Because you can see here, here you will get the magnitude 5 square plus 20 square, right? And VB dash, we calculated VB dash, this one. So it is 10 square plus 15 square. So it is 10 square plus 15 square. So let's solve this. You will get 25 here, 2 to 4, so 400 here, 100 here, and 225 here. So you will get 500 plus 250, it is 750 joule. Okay, so initially you can see the kinetic energy is larger as compared to the final. So the difference in kinetic energy, how much kinetic energy was gained or lost in this collision, this is what they are asking. So change in kinetic energy, so kinetic initial minus final. So initial is equal to 1250 and final is equal to 750. So you will get 0 0 and here 500. Okay, so this is the answer of your problem, 500 joule. So initially it is large, finally it is less, so it means that this much kinetic energy lost. Okay, this much kinetic energy lost. We have our third question. Third question says, an object with a mass m, speed v explode into two pieces, one 3 times as massive as the other. The explosion takes place in gravity-free space. The less massive piece comes to rest. How much kinetic energy was added to the system in the explosion? So this is an important question. By the statement it looks nice, but the calculations is very tricky, so you need to calculate it nicely. So the situation is drawn already. So what it says, we have a mass which is moving with some velocity v. So this is before the explosion, so we can easily calculate the momentum initially, m multiply v. So after the explosion, what will happen? We have a smaller mass and a larger mass. So according to the question, the larger mass is 3 times the smaller mass. So that's why m2 is equal to 3 times of m1. If m1 is equal to m dash, so m2 is equal to 3 times of m dash. And after the explosion, it is also given that the less massive piece comes to rest. So that's why less massive piece is at rest. And the other one is moving, let's say, with velocity of v dash. So how much energy was added to the system in the explosion? We need to calculate. Okay, let's start with the conservation of mass. So by the conservation of mass, the mass initially, the mass is m, and finally it is m1 plus m2. So m is equal to m dash plus 3m dash. So m is equal to 4 times of m dash. So m dash is equal to m by 4. So from the conservation of mass, we get the value of m dash, right? Okay, now we can apply the conservation of linear momentum. By the conservation of linear momentum, so once you apply the conservation of momentum, what you will get? So initial momentum is equal to, you have seen, m times v dash, and the final momentum is equal to m2 v dash, because m1 is at rest. So m times v is equal to, m2 is equal to 3 times of m dash and v dash. This, what is the value of m dash? We can put from our equation number 1. So mv is equal to 3, m dash is equal to m by 4, v dash. So here you can cancel m and m. So v dash will be equals to 4v by 3 equals to v dash. So this can be our equation number 2, okay, which is from the conservation of momentum, 4v by 3. Now based on the kinetic energy, the initial kinetic energy or the final kinetic energy, you can simply say the final kinetic energy, because we know the initial kinetic energy 1 by 2 mv square. So kinetic energy initial, so k initial is equals to 1 by 2 mv square. What about the final kinetic energy? Final kinetic energy is equal to half, that is mass 2 and v dash square. So 1 by 2, what is the value of mass 2? It is 3 times of m dash and v dash square. So we calculated the value of v dash, which is equal to, in our equation number 2, it is 4v by 3. So 4v by 3 square. Let's put the value of m dash. So the value of m dash is equal to m by 4, and square it is 16v square by 9. So this is very important. This is the very tricky calculations, so you need to keep in mind slowly, step by step, put all the values, suitable values. So this will become 3, or you can cancel 4 here and 4 here and 3 and 3. So you will get 4m v square divided by 3. So it is 4 mv square divided by 6. Okay. All right. So this is our final kinetic energy. So what is the change? So change in kinetic energy. Change in kinetic energy, you can write final minus initial. So 4 by 6 mv square minus 1 by 2 mv square, which can be written as, you can take the common values, 4 by 6 minus 1 by 2 mv square, something like this. So let's try to solve. So you get 6 and this is 4 minus 3, okay, mv square. 4 minus 3 is 1 by 6 mv square. So this is your required answer. This is the required answer. So what is this answer? You can write is, this is your answer. So this is all about today's lecture. So we discussed 3 numericals, step-by-step calculations. I hope you enjoy this presentation. You understand the concept, how I solve, how I read the question and apply the basic concepts of conservation of linear momentum and conservation of mechanical energy sometimes. So I hope stay with this channel. If you are new to my channel, please subscribe it and share with your friend. Wish you all the best. Bye bye.